Hello Stormwater designers and welcome back to Clear Creek Solutions hydrology education videos. Today we're going over flood probabilities and planning. This is a very important part of hydrology, especially when you're getting to hydrographs, design of certain facilities, graphing them, determine the probability of events or the frequency of events. This definitely comes highly into play. So it's going to be an important lesson here, doing a brief overview of this and going into a bit about probability. So a quick introduction. So all the projects are planned for the future, and the planner is uncertain as to the precise conditions to which the works will be subjected. The structural designer knows the intended loads for the structure, but he has no assurance that these loads will not be exceeded. He or she does not know what wind or earthquake loads may be exerted on the structure. So this uncertainty is countered by making reasonable assumptions and allowing a generous factor of safety. So you can't know for certain what kind of flood you're going to get, what the max flood is, what the max amount of load is going to be, or a hypothetical earthquake or windstorm that can occur. So you have to then rein it in and make a reasonable assumption about what these high level events could be, what's the probability of them occurring, and then planning in a certain way so you can account for whether these events may occur and can your structure withhold those strong events. Obviously, there's events that will destroy your structure, but we're hoping that the probability of these events are so small that it'll never actually occur, because the loads and how you would have to design your structure to get it to withstand that much force would be completely unfeasible. So you have to find a middle ground to where you're accounting for enough of these heavy events or these large events to make sure that the structure lasts a certain period of time without designing it completely unfeasibly. So the water resources engineer is less certain of the flow that will affect the project. The water requirements, benefits, and costs are all uncertain to some degree, but a serious error in the estimates of the expected hydrology can have a devastating effect on the economy of the entire project. Since the exact sequence of stream flow for future years cannot be predicted, something must be said about the probable variations in flow so that the plan can be completed on the basis of calculated risk. So that's why we're going to go into the probability of certain hydraulic events, rainfall events, flood events, etc., because determining these probabilities is going to help us with our final designs. So let's go into annual flood series. A widely used data set for probability analysis is the annual flood series, the highest instantaneous flow rate at a given gauging station for each year of the flow record. By grouping rainfall data into class intervals, the information may be presented graphically or as a frequency histogram. The histogram gives a picture of the distribution of flood magnitude, and the integrated histogram is a plot of the total number of floods above the lower limit of class interval and is more instructive. So in order to have a representative sample, there ought to be at least 30 to 40 years of record in the data series. And in software we use in Western Washington, there can be up to 50 or 60 years of record. The more record, the better, because we can account for more different kinds of events. Shorter records rarely will provide a representative sample. If hourly rainfall data are available, the annual flood series can be extended using the unit hydrograph method or by a computer simulation, in such software that we use, of course. A reliable analysis requires that all data in a series be gathered under similar conditions. The construction of the reservoirs, levees, bypasses, or other works that might alter flood flows on a stream results in a non-homogeneous series. If the change caused by the works is large, an analysis may be limited to the period before or after the change, depending upon the purpose of the study. A study of natural flood conditions would be based on data collected prior to the change, while a forecast of future conditions would utilize data from one period to the construction. An alternative would be to adjust the data from one period to conform to the conditions existing during the other portion of the record. Isolated flood events distorted by unusual occurrences such as failure of a dam or levee should be omitted from the series or adjusted to conform to the remainder of the data. So we want to throw out really distorting or unusual occurrences so we don't alter our evaluation. The recurrence interval is defined as the average interval in years between the occurrence of a flood of specified magnitude and an equal or larger flood. The nth largest flood in a data series has been equaled or exceeded m times in the period of record. N years in an estimate of its recurrence interval T sub r, as given by the Weibull formula, which is a distribution formula for probability and statistics, is given as T sub r equals n plus 1 divided by m. Several other formulas have been suggested for the calculation of recurrence interval or return period, and so the disagreement between the various formulas is limited to the larger floods where m is small. If m equals 5 or more, the calculated values of t sub r by all methods are almost identical at that point. This equation can be used to define plotting positions, which provide a good estimate of flood flows with return periods of less than 20 years. If an event has a true recurrence interval of t sub r years, then the probability p that it will be equaled or exceeded in any one year is p equals 1 over t sub r. Since the only possibilities are that the event will or will not occur in any year, the probability that it will not occur in a given year is 1 minus p, right? So that's basic probability right there. From the principles of probability, the probability j that at least one event that equals or exceeds the t sub r year event will occur in any series of n years is j equals 1 minus p raised to the nth power. And so here's a few more equations. So then the equations can be derived as follows. P is the probability of the occurrence. 1 minus p is the probability that the event won't occur. And then 1 minus p times 1 minus p is the probability the event will not occur in 2 successive years. And you can go on and on with the power there. 1 minus p raised to the third power is the probability that the event will not occur in 3 successive years, and so on. So 1 minus p raised to the n is the probability that the event will not occur during a span of n successive years. So j equals 1 minus p raised to the n is the probability the event will occur during a span of n years. And we have some sample problems here. So this is a recurrence interval chart based on t sub p or t sub r and going across 1 year, 5 year, 10, 25, 50, 100, 200, and 500. So here's our first sample problem. What is the probability a 50-year flood will occur over a period of 4 years? So we have j equals 1 minus p raised to the nth power. And so we go the probability 1 divided by 50. So 1 minus 1 divided by 50 raised to the fourth power, and then 1 subtracted by that equals 0.0776, or 7.76% chance the event will occur. And then what is the probability a 30-year flood will not occur in 2 successive years? So then we do the same thing. 1 minus 1 divided by 30. We're using this equation here, actually, the 1 minus p times 1 minus p equation. Remember, we want to find the chance that it will not occur. And so a 30-year flood will not occur in 2 successive years, a 93.4% chance of not occurring. So that's our overview of annual return periods and probability. Remember, we have a hydrology terms guide. It's 100% free. It's about 4 pages of basic hydrology terms if you want to brush on those for any exam you have coming up, or just get a refresher. You can download that in the description box down below, 100% free. Anyways, we'll see you guys next time.